Let's continue with our discussion of domain and range. Now we've talked about representing functions and relations in 5 different formats: T-charts, mappings, and list of ordered pairs, which we've already discussed, and also graphs and equations. So this video clip is about finding the domain and range when you're looking at graphs. Now we're going to also use this video as a way to review our families of functions because that's an upcoming lesson. So we're doing double duty with this one video. So if you look at this first function right here, do you recognize that this is just a step function? It is exactly what it looks like it is. And then we've actually seen graphs like this in class. And remember, I'm tracing it right now. I could count 1, 2, 3, 4. This is specifically a quartic function. But if you wanted to generalize beyond that, a quartic function is a type of polynomial function. So if I ask you a question like this later, I would accept either answer. Quartic is more specific, polynomial is a more general answer. And then last but not least, what type of functions have horizontal asymptotes but not vertical asymptotes? This is exponential growth, so it's just an exponential function. And again, you could be more specific if you wanted to and say it's an exponential growth function, and I would accept that. Now, let's look at the domain and range. So, when you're looking at domain, what you want to do is begin tracing the graph from left to right. And so, on the step function, when I trace from the left, I notice the graph starts here, and it goes continuously from x equals 0, but not including 0, all the way to x equals 2. And every point is covered from 0 to 2. Well, the graph is discontinuous. Does that mean that I have a break in the domain? Not necessarily, because the next step picks up at 2 and goes continuously to 4. The next step picks up at 4 and goes continuously to 6. The last step goes from 6 and picks up continuously forever. So the best way to write the answer for this question is to use, in my opinion, an interval notation. So the leftmost x value that I use is 0. 0 isn't a solution, it's just the left-hand boundary. And then all x's forever and ever to the right of that are used. In my opinion, that is the best way to write it. You do have another option. You can say, well, let me describe the set of all x's, so curly bracket, and then you list, or you say, I'm fixing to describe the list of x's, and you would say, any x that's larger than 0 is in the domain. So either one of those is fine. You get full credit for either one as long as your notation's correct. Now the range, you would do the same thing, but you're moving your way from the bottom up. And I notice on this one, what if, I'm going to try something here and see if this will help you see what's going on. I'm going to use the pink line that I've just drawn just to show you what it looks like when I move from the bottom up. So as I'm moving from the bottom up, the first y value I get to is 5. There's not any point in here that the graph takes on, so then the next y value that I get to is 10. So when I'm looking at it, then the next y value that the graph touches is 15. And the next y value the graph touches is 20. So on this one, I don't have a range of y values. I just have 4 specific y values. And so I just need to list the 4 specific y values by saying it's the list which includes the y value 5, the y value 10, the y value 15, and the y value 20. Why can I not do something like 5 to 10? because that means the interval takes on every single y value between 5 and 10. But is there a point on the graph whose y coordinate, for instance, is 8? 8 is between 5 and 10. I didn't mean 5 and 10. I meant 5 and 20. My bad. But no, 8 falls between 5 and 20, but there's no point in the graph that has a y coordinate of 8. So the interval is too inclusive. It includes too many y values. So instead, it's better to make a list. So I think I'm going to pick up and look again at the domain. I'll use highlighters when I'm using the domain, so hopefully you can follow me. So I noticed that this quartic function starts on the left side. It goes all the way forever to the left. So it goes to negative infinity on the left. And I'm tracing it, and I'm trying to see, are there any holes in the graph? Are there any jumps in the graph? Are there any vertical asymptotes in the graph that keeps my domain from being just all real numbers? Well, nope. I have traced from one side of the graph to the other side of the graph, and there's no breaks or pauses or anything else. So I'm ready to just say that means the domain is all real numbers. Now, another thing you could do, if you like the interval notation, is you could say negative infinity to positive infinity. But what I'm listing first would be my natural tendency as to how I would answer it. All right, so when I look at the range, I'm going to get my handy dandy pink line here. These arrows say that the graph points forever downward. So I'm moving my line up, 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 up. So again, every single place that my y pink line is, I am touching y values that are picked up by the graph. So far I've got every y value possible. So again, my pink line continues to touch y values picked up by the graph. And then I get to here, and suddenly notice that my pink line is up here, and there's no point on the graph with that y value. So here the range is not all real numbers. Well, again, in my opinion, it would be best to say, well, the y values that are used go from negative infinity all the way up to the highest point on the graph is here. And that's at y equals 3. That's the top. Whoa, that is not what I meant to do. That's the top y value that we've got. Now, the other way to write this is you could say it's the set of all y's such that y is less than or equal to 3. So if you prefer this notation, that's fine. Just make sure that whichever you use, that your notation's correct. Now, last but not least, if we move to the exponential function, again, I start on the left, and I can see this one goes to negative infinity on the left. Again, I'm looking for breaks in the graph, holes, jumps, or vertical asymptotes. So I can trace from the leftmost end to the rightmost end without pause. That means, again, that the domain is all real numbers. And you know that you could say negative infinity to positive infinity if that was your choice. So I'm going to get my handy dandy pink line. And notice from bottom to the green asymptote, I'm covering all kinds of y values that the graph never takes on. So that means, again, that the range is not all real numbers. And then I'm going to cover from there up, and from here on up, my pink line will always be touching a point on the graph because of the arrow. So even though I don't obviously have it graphed that high, the arrow indicates that it would continue to go. So my range on this one is bounded on the lower end. So the lowermost boundary is 2. The graph doesn't actually touch. There's not actually a point that has the coordinates whatever, comma 2. So I have to use a parentheses. And then the y values are going to continue to go upward forever, and there will be a point in the graph with those y values. So let's do about 3 more examples. I'm going to try to use handy dandy technology magic and see if I can make this work. There's a go. So I'll use that whole pink line thing on these. Now, before we get started on domain and range, let's again look at families of functions. Do you remember last year the type function that you graphed that was often in 2 or 3 or maybe 4 different sections like this one is? And you were supposed to find the x-intercepts and y-intercepts, and you always had to decide where the vertical asymptotes were and if you had horizontal or slant asymptotes. Hopefully, rational function is coming to mind. Rational functions are those that tend to have both horizontal or slant asymptotes as well as vertical asymptotes. And so the second function here that I've got, if you can see me tracing it, it's kind of like a polynomial function in that it's wavy, but it's not, because polynomial functions are irregular in their shape. This one's very uniform. So for instance, I have the top of my wave 2 units high, 1 unit over and I hit the axis, 1 unit down and I hit the min, 1 unit over and I hit the axis, 1 unit over and I hit the max, 1 unit over and I hit the axis. So notice that each wave is 2 tick marks wide, and each wave is either 2 tick marks high or 2 tick marks low. When you have a function that's repetitive that way, there's a uniform pattern that you can follow. That's a type of trig function. And this more specifically is either a type of cosine wave or sine wave. We'll talk more about that when we get into trig so you can identify. But any one that repeats itself in a very, very predictable uniform pattern is a trig function. Now, this bottom graph that's in 3 different pieces, it's not rational because it doesn't have vertical asymptotes and horizontal asymptotes and all that stuff. And remember, this pink line right here is not part of the graph. It's my pink help you see the range line. But all this function is a piecewise function. Where I've taken pieces of different functions. So you might recognize that the first piece is a piece of a quadratic function. The middle piece is a piece of a linear function. The third function is actually a piece of a cubic function because it would come on down like that. But anyway, that's not necessary for you to know. But, you know, if you just piece together parts of different functions, you call it a piecewise function. Now notice on my first rational function, when I'm looking at domain, I could definitely say the domain starts at negative infinity, and what it does is it's going to go all the way to x equals -3, but then there's a pause in the graph. And when I have to jump over the vertical asymptote to start again, it starts at -3 and goes all the way to x equals 1. But then there's a pause. I have to lift my pencil and then start tracing the third piece, which goes all the way from 1 to infinity. Well, what I said is actually what you could write for domain. But I would prefer instead, this is one time I like the alternate notation better. It's actually a little bit shorter to say, I want to use the set of all x's except there is no point on the graph on this horizontal asymptote. No point in the graph has an x coordinate of -3. So I'm going to say all x's except x equals -3, and the same is true for x equals 1. So that's the notation I would use if it were me. But you could also say negative infinity to -3, union -3 to 1, union 1 to infinity. And then you're giving the individual domains for the 3 individual pieces of the graph. Range. Let's see if I can do that again. Now, I can see that both the first and the middle portions of the graph go all the way down to negative infinity. So I've got all my y values there. Go back. And then when I come all the way up, now the first and third portions of the graph are bounded either below or above this pink line, but the middle portion of the graph gets that y value. So notice the middle portion of the graph covers all y values from negative to positive infinity. So the range is all real numbers. All right, so on the trig function, domain, we're going to start on the far left piece. So notice it starts on x equals -1. We're tracing. There's no pause, no break in the graph, no reason to lift your pencil. So I trace all the way to x equals 1, 2, 3, 4, 5, 6 without stop. So this one, the domain just goes from -2 to +6. You could also say, although I probably wouldn't, x such that -2 is less than or equal to x is less than or equal to 6. That may not be my preference, but if that's your preference, that's completely okay. Now, do you see that the range is similar in that it's completely bounded the same way the domain was? If I get my pink line, then the lowest y values that touch the graph, the pink line as I'm coming up, are at y is equals -2. The graph touches every y value somewhere on the graph all the way up to y equals +2. And then above that, the graph doesn't touch any more y values. So I would probably just say the range is interval notation -2 to +2 bracket. You could also write it similarly as we did the x notation, except you would say all y's such that -2 is less than or equal to y is less than or equal to 2. All right, so one more domain and range question. On the piecewise function, the leftmost piece shows that the arrow points left. So my domain's -infinity all the way to, now it comes up to x equals -3. I have to pause, but does that create something, an x value that I pull out of the domain? No, because the middle piece of the graph runs consistently from -3 to +2. Well, do I have a problem there? No, because the third portion of the graph runs consistently from 2 forever and ever up, but also to the right. So even though my piecewise function is very discontinuous, the domain does not leave out any x values. So when I look at range, if I start at the bottom, of course, I can see that since the graph doesn't touch my pink line down here, that the range is not all real numbers. So my lowest y value is picked up on the right piece of the graph. When I get to here, my pink line is touching the right piece of the graph and the middle piece of the graph. Here, my pink line is touching all three pieces of the graph, but that doesn't really matter. What matters is the right piece of the graph and the left piece of the graph go for an ever and ever upward. So really, my right piece of the graph is the most inclusive where the y's are concerned. So I'm going to say the range is going to be from the very bottom y, which I see at -3, forever and ever upward. And of course, you could say y such that y is greater than or equal to -3. You'll see that when I flip the slide, we're getting into equations. That means you're ready to do part 2 of A8.